I am very excited that we finally have this launch, but then we have to wait another 1 or 2 years until the first data will be published. Of course, we are not waiting. We are not waiting in our offices, but we are actually working hard because there is still a lot of things that we have to do, especially, but not only, but especially on the theory side where I'm working. My name is Aurel Schneider. I'm an Excellenza professor at the University of Zurich, and I work in theoretical astrophysics and cosmology.
Euclid is a space telescope, ready for its journey into space. It will scan the sky, mapping the whole universe, showing the unprecedented huge amount of galaxies, and bringing light to dark matter and dark energy. It will reconstruct 10 billion years of cosmic history. Euclid is an ESA mission. UZH scientists are part of the Science Working Group.
So I've been part of Euclid for a bit more than 10 years now, and I'm working on the theory side, mainly working with numerical simulations, and we try to predict the signal that Euclid will measure. And this interplay between predictions and observations, between theory and observations, is very essential in science because we need the theory to interpret the data, and on the other hand, we need the data to confirm or rule out the theories that we have. I am mainly interested in how matter clusters in the universe to form galaxies, gravitationally bound objects. This is a very complex process that requires large simulations, and we need these simulations to understand how the initially smooth universe starts to cluster and transform itself into dense clumps, which are the birthplaces of stars and galaxies. This process of structure formation requires one very important component, which is the hidden dark matter. Without the additional pull of this dark matter component, it's impossible to form the amount of galaxies that we see, for example. And one of my main research goals is to better understand what this dark matter component exactly is. And I'm using astronomical observations to do that. And Euclid, the Euclid Space Mission, is an ideal probe to try to understand how structure formation happens and what the exact role of dark matter is. Today we are certain that we need dark matter in order to explain the universe. We are also fairly sure that this dark matter needs to be some kind of new particle that would extend the realms of physics. What we don't know is how this particle behaves. For example, these particles could be very massive, or they could be very light. They could be very cold, meaning that they're not moving around much, or they could be warm or hot, meaning that they have higher velocities. They could also bump into each other, or they could be completely collisionless. These are the type of things that we want to figure out with Euclid. The other thing that is interesting is that the dark matter paradigm could be either just one more boring particle, or it could be a whole set of new particles that interact with each other and build a dark sector. About 10 years ago, a bit more than 10 years ago, the European Space Agency launched another satellite called Planck, which was a very successful mission that measured the very large scales of the universe at early times. With Euclid, we want to go further than that and go now to scales that are much smaller and that are much closer to us. And by pushing to smaller scales, we can try to find something new. Because whenever you push the limits of knowledge in one direction, then we hope to find something unexpected there. In terms of dark matter, the small scales are particularly interesting because these are the scales where we expect the largest differences between the different models. For example, if you look at the clustering, at how strongly different dark matter models cluster, then you see differences at scales that are not accessible by Planck, by the former space mission, but they will be accessible by Euclid. And we hope to find small differences in structure formation that can tell us which of the dark matter model would correspond to what we have in the universe. And we are very excited about the results that will come soon and how they match our theoretical predictions.
Euclid will be launched in July 2023 and travel to its destination, the Sun-Earth Lagrange Point 2, 1.5 million kilometers away from Earth. The first raw data from Euclid is expected to be available in 2024.